Welcome back to yet another LeetCode easy problem. We're currently practicing the interview process more than trying to solve difficult problems. Have a look at the previous videos to understand how the structure is, how we approach the problems. You probably need to only watch like the first 30 seconds of any of them. And to understand what we do. So today we have a problem that I haven't tried before. It's LeetCode 3222. Find the winning player in a coin game. I know there are a couple of variations of this theme in other LeetCode problems, but with different difficulties. This one is an easy variant. Let's check it out. So we're giving two positive integers x and y, denoting the number of coins with values 75 and 10. Okay, so two coins, values 75 and 10. Alice and Bob are playing a game. Each turn, starting with Alice, the player must pick up coins with a total value of 115. So since one is 10, we always must pick up 175. We cannot pick up 2, because then we're over 115. So 75 plus, how many more? How many more? 4. 4 more to get 10. So 75 plus 40 is 115, right? If the player is unable to do so, they lose the game. Okay. Return the name of the player who wins the game if both players play optimally. Right. Constraints. Okay, there's just a constraint on the number of coins, but for our runtime analysis, we assume there are no constraints. Otherwise, everything will automatically be constant space and constant time. Let's have a look at the examples. Input x1, so that means x is 2. That means we have 2 coins, value 75, and 7 coins of value 10. And Alice starts, right? Oh, wait a second. So they have to pick up coins with a total value. Well, it doesn't say whether they have to pick up coins with a total value of 115 every turn, or if they pick one coin at a time. But the example now clarifies that Alice picks one coin with a value of 75 and 4 coins with a value of 10. So Alice wins because she's the first one to do so. Okay, so in one turn, she can pick up, well, she has to pick up the 75 and try to pick up 4 times 10 as well. And because she's the first one, she wins. Okay, cool. So it's not the first one who can't pick up 115 who loses. It's also the first one who picks up that value who wins. Is that right? Because we have 2 coins of value 75. Oh, I see now. So Alice picks 75 and 4 of the 7 tens. And then Bob, is it Bob? Bob can't pick up 4 coins with a value of 10. That's why Bob is losing. He can't move. Okay, I get it now. Second example, we have 4 coins with a value of 75, 11 coins with a value of 10. And now Bob wins because Alice picks 1 of here, 4 of here. Then the next turn, Bob picks up 1 of the 75s and 4 of the 10ers. So that means there are only 3 remaining and Alice can't pick up another 4 coins. And so that's why Alice loses and Bob wins. Okay, cool. So yeah, this is kind of a little bit like a math problem. I mean, you can iterate and you can implement like an iteration where in each step you let each of them draw. And maybe we should just do this just for the sake of completeness. But there's also a solution where you can calculate this directly. And so let's try the brute force one first. Let's try that one first. And yes, and the runtime and space complexity, I'll do it after in this case. So while true, well, basically while x is larger than 1, we need to have at least 1 coin with a value of 75, and y is larger or equal than 4, larger or equal to 1. So this is a precondition for somebody to draw the coins, right? And then we just subtract one of the coins from X. So we decrease the count of the coins with a value of 75, but we also decrease the count of the coins with a value of 10, and we know we need 4. So, and we say winner, and the winner is going to be Alice or Bob. By the way, we have to check if that could also be the case where nobody wins. What happens then? So we could have X equals 1 and Y equals 1, then nobody wins. What do we do then? So the problem doesn't really specify it, right? So maybe we have to find out. Maybe the winner is nobody. So maybe we just do this if X is smaller than 1 and Y is smaller than 4. Maybe just return an empty string. Maybe that's the edge case, yeah. And otherwise, we know we're going to have a winner. And I'm just going to do this. So the first one to draw is Alice, right? So she draws. And now the next turn is Bob, right? And just going to reverse our array. And then the last position in the array is the one who was able to draw the coins without issues. So if we run this, we should hopefully get a correct result. Yes, so that's correct. Now if we submit this, let's see if we guess the edge case of no winner correctly. Yes, we did. Okay, very nice. So yes, so this obviously we have certain time complexity and of one space, right? We only have this as our winner array. So what is the time complexity? Well, we are subtracting something from the X and the Y. So it depends on the value in X and the value in Y. So it's basically Y divided by 4. That's how many times we're going to iterate through the loop. And it's going to be the minimum of that X and Y divided by 4. That's going to be our runtime complexity. Okay, so there should be another way of how we can deal with that, and that is programmatically. So we could right away say, how many turns are even possible, right? Possible turns. And we already have the answer here. That is the number of turns that are possible. And we know that if one turn is possible, we have Alice as the winner. Otherwise, Bob will be the winner. And let's see. And let's see, let me just check real quick. So if Y has to be 4, so if we have at least one turn that is possible, the winner should be Alice. So we'll have, yes, 1 minus possible turns. If 2 turns are possible, that means the winner would be Bob. So 2 turns modulo 2 will be 0. So 1 minus 2, index 1 is Bob. If 3 turns are possible, we're switching back to Alice, right? So that should work as well. And this solution is now O of 1 time and space. Time and space. And yeah, that's an example of how you run into the optimal solution by doing a non-optimal one first. Now, really, the runtime complexity of this non-optimal solution gave us the way of how to basically implement the optimal solution. Correct on the test case. Let's submit it to see if all test cases pass. Yes, hooray! So that's how we've done it. And well, better than constant space and constant time is not possible. So we don't even want to look at other people's solution, but maybe we do. Maybe they did something cool. Iterative and recursive solution O of 1. That's not O of 1, is it? No, it's not. It's dependent on the size of x and y. So that's not O of 1. That's log of something. That is O of 1. Oh, yeah. So that is O of 1. That's another way to write it. Or you could do that. Actually, yeah, let's do that. Why not? And it looks like they don't even check the edge case, so maybe we don't have to do that as well. So we just return that, and we calculate the offset with that. And 2. That'll be the index that we're looking at, and we have to reverse. Do we have to reverse? Yes, I think we have to reverse this, if I'm not mistaken. Yes, we did. So yeah, that's another way of doing it. Cool. Anyway, enough of that. Thanks for watching. I hope you've enjoyed this, and check out some of the other videos, or at least try the other problems that are listed in the videos, and then compare your solution maybe against the one that I found. You'll also see that in my solutions, not all of them work out right away. So there are some interesting things to learn from them as well, beyond just finding a solution. Thanks.